So yeah, we talked on Friday about redox reactions in acidic conditions. So we learned kind of the step-by-step process. That really is the same process on every one of these problems. If you know how to do those steps and memorize the order, I think these really aren't too bad. And what he's going to talk about tomorrow is how we're going to do these if we're in basic conditions. And so I'm going to walk that through with you guys here. I'll probably try to see if you guys can do this first one a little bit more on your own, and then I'll go through the second one and kind of introduce the difference with this process, but it's only one step that's different. And then since your guys' quiz is Wednesday, Thursday, right? Okay, I'll probably put like a extra worksheet out maybe on Tuesday night or something to give you guys more practice, but this will be the cumulative quiz review for now. But yeah, so if you guys want to do this first one up here, we have a chemical equation for an entire redox reaction, right? So we have one of these things is going to be reduced as it goes from a reactant to a product, and one of them is going to be oxidized as it goes from a reactant to a product. And um, I can kind of go step by step up here, or you guys can take the wheel if you want. You guys feel good trying this one? Want me to do it? I'll do it. All right, perfect. Like I said, I love this stuff. This is one of my favorite things we do. So whenever you get a problem like this and it says balance the following equation, we're on redox unit, so we're going to assume it's a redox. And the first thing you want to do is identify what is being reduced and what is being oxidized. So I'm going to write this out. And this first step is using skills that you developed in Chem 131. So I'll talk about it still, but he's not going to give you any really weird, you know, reactions where you need to memorize that long list of oxidation states. It's pretty standard, and most of the time you'll have an O in there, and the O is kind of the easy thing because we know that O always has an oxidation number of -2. So we have this as a reaction. We can start with the first one here. So I'll kind of walk you through how I do these. Again, we say that O is -2 across the board and has a minus overall, so -1. So that means that overall this compound needs to have an oxidation number of -1. And we have four O's, so 4 times -2 means we're going to have -8. And Mn, we only have 1. So it's going to be X minus 8 equals -1. So Mn has to be what? +7. Yep. All we got to do is some basic algebra here. +8 to the -1. I'll do that again. So we have O is the one that you really should memorize is always -2. And you're going to see this in most of the problems we're doing. So we see this is -2 as its oxidation state, and we have 4 of them. So that means that -2 is going to be multiplied 4 times. So it's -8. And the reason we're having it all equal -1 is because, again, MnO4 has the -1 ionic charge. So do we feel good about that? Well, let's try this next one. So again, O, what's its oxidation number? -2. Yep. We have 4 of them. So again, we have 4 times 2, meaning -8, equals, this time it's 2 minus, so it's going to be equals -2. And now we have 2 of these carbons, so that's kind of the last thing we're looking for. So I'm going to put a 2x here. So 2x minus 8 equals -2. So if we do that algebra, we would add 8 to both sides, and we get 2x equals 6. 6 divided by 2 is 3. So we know that C has a +3 as its oxidation state. Are you feeling okay with this? Mn2 plus, this one's easy. 2 plus, +2. CO2, this is a neutral compound, so we're going to keep it equaling 0 overall. Again, O is -2. We have 2 of them, so it's -4. X minus 4 equals 0. So carbon here has to be +4. This is the first step on these problems. Now we need to see what is being oxidized, what's being reduced. So as a reminder, what is oxidation? The loss of electrons. Yep. So if something's oxidized, it's getting more positive. Reduction is the gaining of electrons. So I always use this. It helps me. Oil rig. Oxidation is loss of electrons. Reduction is gaining of electrons. There's also like Leo the lion goes grr. I don't know. There's a few different ones they tell you in 131. This one always stuck with me. So we look over here, and again, we know O is not going to be the thing that's getting oxidized or reduced because it's always -2. But Mn is +7 as a reactant and then +2 as a product. So what would we say is happening to Mn as it goes from a reactant to a product? It's gaining electrons. Yep. So it's being reduced. Yep. So I'm going to write, so we can separate them into the two half reactions. That's what I'm doing now. We want to have a half reaction for what's being reduced and then a half reaction for what's being oxidized. So I'm going to write MnO4 minus, and I'm going to leave a lot of space because there's a lot of things we got to still do. Goes to form Mn2 plus. So then we know the other part is what's being oxidized, but let's make sure real quick. We have C going from +3 to +4. That means it's getting less negative, meaning it's losing electrons. So that's what's being oxidized here. Exactly. Yep. So let's start with the top one. Let's do the reduction one. Doesn't really matter where you start, but we know that there's a very important order of these steps. You can't go out of order or else everything kind of gets messed up. So what's the first thing we want to do here? What's the first step? That's going to be actually the last step. So we'll get there, but the very first thing we do is balance things that are not O's or H. And so that means we're taking a look at Mn, manganese, I think. And there's one of both. So we're good there, right? There's the 2 plus doesn't matter for that. We're only talking about the coefficient. And so now we're going to start balancing the next thing. So the next step would be balancing the O's. So we have 4 on this side, none on this side. So what are we going to add over here to balance that? Or yeah, H2O specifically. So we can't simply add oxygen by itself because all these things are happening in water solution. So we can add water. So we would add 4H2O. And now the next step is balance the H. So we have how many on this right side? We have 8 now. Yeah. So we have to always multiply this by the subscript 2. So that means we have to add 8 protons to this side. And this is where we're going to talk about how we're doing this in acidic conditions. And so the fact that we're in acidic conditions mean we have a lot of hydronium ions floating around. So we can do this. That's fine. It's not messing with anything. I'll show you in the next problem what happens when we're in basic. But for now, this is good. And now we're getting to the electrons part. So we've balanced everything in terms of coefficients and atoms. Now we need to balance it in terms of ionic charge. And that's what's kind of unique about this as opposed to what you guys are doing in 131. So we have 8 plus and 1 minus. So the reactant side is what overall? +7. Is that okay? So we have to count up everything that has an ionic charge on both sides. So if there's 8 pluses and 1 minus, that means overall this side is going to be, I'll write it kind of up here so it doesn't mess with stuff, +7. Over here, the water is neutral, so that doesn't do anything. And we have 1 of this manganese 2 plus. So the right side is +2. And we can't add positives, so we're not going to add like +5 of some positive thing. This is the only species on the right side that has any ionic charge. So this is where we add electrons. We can add electrons. And so first off, what side would we be adding it to? Left. Yep, we're adding it to the left because this side is more positive. And how many would we add? 5. Yep. That's all we do here. And then the next one, this one looks maybe a little bit easier. We'll see. We have, and again, you go to the next half reaction before we start doing the complete, like balancing the entire thing. So we'll start here now. First step again, what is it to balance? The atoms, which ones? Yeah, anything that isn't O and H. That's what we're starting with. And this time we do need to do something because we have 2 carbons on this side and only 1 here. So we're going to add a 2 in front there. So that step's done. Now we're going on to what atom next? O's. Yep. So we have 4 on this side and 2 times 2. We have 4 on that side too. So we're good there. And then this is where we would worry about adding any H's. If we had already added water, we haven't. So we're good here. We can go straight to the electron step now. And what are we thinking? Are we first off adding electrons to the reactants or products? Products, yep. And how many do you think we're going to be adding? 2. Yep. So we have a 2 minus here, and there's no coefficient, so it's really only 2 minus. And this is totally neutral, so we have to add 2 electrons here. And now this is balanced entirely. And so a good thing to like kind of pause and think about, yeah. Because when would we have needed to add any O's?
Oh yeah, we did.
That's the reason. Yep. No, you're good. So since we had 4 here and 4 here, that step is done. We're good to go. Yeah. If you ever do one of these and you find out that your electrons are not on opposite sides, you messed up. So we're good here. The electrons for this one are in the reactants, and the electrons for this one are in the products. That's necessary. Yep.
Reduction reactions or
Mhm.
on the reactant side?
Yeah.
Or on the reactant side?
It should. Yeah. Let me not be quick to say that, actually. I don't know. I think um, if it's getting, well, the answer is probably yes, but I would have to like think about it a little bit more. Not sure. Um, but now we need to do the next step kind of before we completely combine these two together. And what's that going to be? Cross out the electron specifically. So the whole point of this is that we can get the same number of electrons on both sides so that they can cancel out. And this goes back to like 5th grade, 6th grade math when we had the lowest common multiple. So doesn't matter if you don't remember that. All you need to know is that we have to find something that 2 and 5 multiply to, and we want to find the lowest number that is. So yes, exactly. So if we have 5 here and 2 here, what number is the closest multiple of those two? 10. Yep. So we can multiply this whole entire thing up here by 2, and this whole entire thing here by 5. And I'll do that up here. So we have 10 electrons plus 16 protons plus 2 of the MnO4 minus going to form 2 Mn2 plus and 8 waters. And then over here, we're going to get 5 of the C2O4 2 minus, 10 carbon dioxides, and 10 electrons. So I'm actually going to get a different colored pen to make this next step easier to see. I'll use a pencil then. So we have 10 electrons in the reactants and 10 on the products. So that's good. That's what we need. These fully cancel. Now we have 16 protons here, but none on the product side for either reaction. So that's going to have to stay at 16. These species, the like unique ones, will like basically never cancel out. So this is going to stay 2. This will stay 2. A lot of times you can cancel out water, not in this instance, because again, we didn't add any water to the oxidation reaction. So it's going to stay 8H2O. And we find out that there's really nothing we can do here other than canceling those electrons. So now the last step is adding up all of this stuff into one long reaction. So I normally, yeah, you're good. Mhm. You would. So in an example, if we had 8 waters in the product and then the next thing 2 in the reactant, you'd get rid of all of those 2 in the reactant, so would no longer be a reactant, and you'd go down to 6 in the products. Yes, exactly. So this one, we'll start with the top thing. Doesn't really matter the order you do it in. And then we also have the 5 C2O4 2 minus going to form 2 Mn2 plus, 8 waters, and 10 CO2. So Yeah, these take a long time. They're honestly like I would guess he would do a smaller question on the exam, like maybe ask you how many electrons are added to one of these half reactions or something. So you don't need to do the entire process, but it's really good to know how to because he might ask you to do that. And then I'll go through and there's a way that I like to verify that we did everything right. If you have a lot of time on an exam, it doesn't hurt. So we can go through and actually count up every atom on both sides and also the total ionic balance on both sides and make sure that it's the same. So we can try that. So let's say reactants, products. We'll start with the first thing I see, H's. We have 16 H's, and that's it. So 16H. On the reactant side, over here, 8 times 2, also 16, so that's good. Next thing I see is the Mn. We have 2 of them here and 2 of them here. O's, we see 2 times 4, so 8, and also 5 times 4, so 20. So 28 on this side. Is that right? Yeah, okay, good. Over here, 8 O's and then 10 times 2, so 20. So again, 28. That's good. And then the carbons, we have 5 times 2, 10, and 10. And then again, we also can go through and make sure. So we have 16 plus minus 2, and then minus 10, which is a 5 times 2. So 16 minus 12 over here is 14. Let's see, 16 minus 2, 14 minus 10, so 4, plus 4. On this side, we have 2 times 2, so 4 plus, and that's it. So you can always do that. Everything is the same. We did whole thing right. Now, the next one is honestly the same steps to get to most of the problem. There's only one thing that's slightly different. So I'll go through this one as well, maybe a little bit quicker.
That's like the farthest you have to do.
Yeah, that's the like complete problem from beginning to end. Actually, what I'm going to have you guys do, so you have a little bit more practice with this, is do the first part where you're separating these into the two half reactions. So you see what's being oxidized, what's being reduced, and then pause there, and I'll come in and show you the rest. Say again. I'll show you. There's one step that's different, and I'm pretty sure this is what he's doing in class tomorrow.
Do you think this is going to be the other since we feel like another day? Kind of like the
Um, no, I think this is honestly going to be one of the easier ones. The Gibbs stuff, like I think I have a few problems in here about it. Most of that is plugging into formulas, and a lot of those formulas you're given on the exam. So I could see him going a lot more conceptual with this one. So like making sure you really understand entropy, and like why things are getting more disordered. And for that, I would like look through his PowerPoint slides and stuff.
We could go over it like once, you said like.
Mhm. Yeah, I definitely will. Has anyone gotten it yet, what they think the reduction half reaction would be? No worries, keep working. All right. So I'll go over how I, again, break these up into the two half reactions and how I know what's being oxidized, what's being reduced. So we write out the entire thing again, and we go one by one with the different species. So the first one here, again, we know that O is -2, and we have 7 of them. So that means we're overall, it's going to be -14 from the O's, and the whole thing has to equal the -2 up here. So we have 2 of the chromiums. So I'm setting this up as 2x minus 14 equals -2. Does that make sense? Okay. So then we can find that we add 14 to both sides, divide by 2. It has to be +6. And then over here, we have, again, O is -2. This entire thing needs to equal -2 because that's the ionic charge. And then we have 2 of the carbons. And so again, 2x minus 8 equals -2. That's how you'd set this one up. We find that C is +3. And then chromium, 3 plus is easy, it's +3. And then CO2, again, this one is going to be neutral, so it's -2 times 2, so this has to be +4. So then we have to see what's being reduced. And I see over here that the chromium goes from +6 to +3. So it's getting more negative, so it's gaining electrons. So this is what's being reduced. And the other one, carbon is going from +3 to +4. So it's getting more positive. And the other way we can say that is that it's losing electrons. So now we have the setup and we can start doing the other stuff. And so I'll work through this part with you guys. First step is the same as it was on the other one. So we have to balance things that are not O or H. And so this one, we have 2 chromiums here and only 1 here. So I'm going to throw a 2 in front of the Cr3+. Now we go on to the O's, and we have 7 of them here. So what are we going to add to the product side? 7 waters. Yep. And now this is where things get a little different. We said that in acidic conditions, we could add 14 protons to this side, no problem. But we're not in acidic conditions. So we're in basic, which means there's less H pluses floating around and more hydroxides floating around. Yeah, it'll be right in the problem, probably underlined like it is here. So we know that at least we need to balance the H's by adding 14 of them. But what we need to do is add also 14 hydroxides to balance that out. So that's the big difference is when you add an H plus, you have to then add OH minus. And also we need to add those same number of hydroxide ions to the other side. So that's it. That's really the only difference. And you might already have picked this up, but if we added 14 OH minus and 14 H plus, does anyone have an idea what this would turn into? It would be 14 H2O. Yeah, so it'll be OH minus plus H plus is water. So we can really cancel this out and simplify it down to 14 water molecules. But this stays over here as 14 OH minus. That's really important. So we're done there for now. Or actually, let's do the electrons part first. We see that this side is 14 of a neutral species plus this neutral species. So overall, this whole side is neutral. Over here, though, we have 2 times 3 plus. Oh, thank you. Thank you. Yep. Good catch. So this side's 2 minus. This side is 2 times 3 plus, so 6 plus, minus those 14, so -8. So if this is -2 and this is -8, first off, what side are we adding electrons to? Left side, and we'd be adding 6. There we go. So I'll do that. 6 electrons. Yep. The side that's more positive is what's going to receive the electrons. We want them to be equal. So we can't add something positive to balance it out. So we have to add electrons which are negative to balance it out. So then we can go on to this one. It's kind of the same thing we did on the last one. where we have to balance the non-C or non-O's and H's first. And so we have two here, only one here. So I stick a two in front, and now everything is atomically balanced. And so now we can go on and say that if this is 2 minus, we have to add 2 electrons here. That one's not bad. And so now we're getting to the part where we can really start to combine things. What is the lowest common multiple of 6 and 2? 6. Yep. So we don't have to multiply this top one by anything. We're only going to multiply this bottom one by 3. And I'll write that out again. So it becomes 3 C2 O4 2 minus. This one 6 CO2 and 6 electrons. So now we can start doing our canceling. We have 6 electrons here and 6 electrons here. That's good. We need those to be canceled out. Water, we have 14 waters here and 7 waters here. So what can we do there?
Get rid of them on the product.
Yep. So we'll get rid of all 7 of these. And this will turn into, oh my gosh, into 7. Do we feel okay about that? Cool. Let's see, this next thing here, we can't cancel this guy out at all. Can't cancel this guy out at all. We only have the hydroxides over here, so they're going to stay. And same goes for the Cr3 plus and the CO2. So we've canceled out everything that we can. Now we get the last step, and all that is putting this into one big reaction. So I'll start up here. So we have 7 waters plus Cr2O7 2 minus plus the 3 C2O4 2 minus. And then this is going to be 2 Cr3 plus our 14 OH minuses and 6 CO2. Again, I'll do this real quick and go through and make sure we did it right. We have on the left side 14 H atoms. Right. Okay, perfect. And then 14 on this side. Next atom is O. We have 7 plus 7 plus 3 times 4, 12. So that's 26. 3 times 4 is 12, plus 7 is 19, plus 7 is 26. Yes. Okay. And then over here, 14O plus 6 times 2, 12. Yeah, all right, that's 26. Good. Not great at mental math. CR, we have 2 over here and 2 over here. The carbons, we have 3 times 2, 6, and 6. So all the atoms are balanced. That's good. And then last thing, we have 2 minus here and 3 times 2 minus here. So minus 6, minus 8 overall on the left side. And then 2 times 3 plus, so 6 plus, minus 14 is also minus 8. So we're all good there. So yeah, everyone feel okay about that? The only difference, again, with these basic condition problems is that when we add the H plus, we then need to add the same number of OH minuses to that side and the other side. Because if we think about this thing taking place in a bucket of basic solution, we no longer have all those H pluses floating around freely. So the only reason we could do that on the other one is because there's so many H pluses sitting around, we can grab them to make this thing balanced. Yeah. So what we're doing here instead is really adding water, because again, these cancel into water, and we still add that many basic hydroxide ions to the other side. He can probably give a better explanation than that, but that's really it. Okay, let's go back to non-redox stuff. Do you guys feel okay with this stuff? Cool. I like it. It takes a long time, but once you get the process down, it's really the same thing every time. All right, so tell me if these would be a positive change in entropy. So if the delta S would be positive. First one is vaporization of a liquid. Do you remember what vaporization means? Very sciencey way of saying evaporation. So that means we're going from what phase of matter to what phase of matter?
Liquid gas.
Liquid to gas. Yep. So if we're going from liquid to gas, would that be an increase or a decrease in entropy? It'd be an increase. So as some review, when we go from a solid to a liquid to a gas, this is increasing in entropy. And we can think about why when we think of like the particles in these states of matter. Solids, if we think of a block of ice, those particles are stuck in their like 3D matrix. They're really not moving around. Liquid has a bit more movement, but still it's not going to be going too crazy. And then gas particles are everywhere. You know, they're moving rapidly, and they're really kind of creating a lot more of those microstates. That's the science term for it. And so that means we're going to be increasing entropy for all of these. Entropy is the definition that like Google will tell you doesn't make a ton of sense to me. It says the amount of disorder in a system. And that, again, that doesn't mean a whole lot to me. I think of it as how rapidly and wildly the particles are moving, pretty much. So like, if you think about something like a solid, again, those particles are really contained. They're not very disordered, if that makes sense. They have a fewer number of microstates. So there's not as many individual states where you could find those particles sitting around. As you go to a gas, the microstates is increasing, and there's way more possible combinations of where those particles could be.
So more disordered would be a gas.
Gas is more, yep, disordered than solid or liquid. All right, how about this next one? A salt dissolving in water. What do we think? Would that be more or less?
Yeah.
More. Yep. So again, same concept. Salt is a solid. It's very much in that tight, like, matrix of particles. As it goes into water, it turns into aqueous, right? So we would have aqueous sodium ions and aqueous chlorine ions. And once we have that, those are floating around in solution, now moving a lot more, bumping into one another. They're more disordered. So that one's also going to be positive. How about the next one? Formation of liquid water from hydrogen and I didn't need to say it twice, and oxygen in their elemental states. This one is like really kind of an annoying way of wording it. So I'm sorry. But in their elemental states, does anyone remember what hydrogen and oxygen are? What phase of matter that is? Gas. Yep. So this is a really annoying way of me asking if something's going from a gas to a liquid. Would it be a positive or negative delta S? Negative. Yep. There you go. Next one, a condensation reaction. Negative. That's the same exact thing, right? Gas to liquid. And then fusion. Does anyone remember what fusion is? Super annoying sciencey way of saying melting. So if an ice block melts into liquid water, it's fusing. I'm like 85% sure about that. Let me make sure.
That would be increase.
Yes, that would be. Good. All right. I didn't lie to you guys. So yeah, this one would be a positive delta S. Does that make sense to everyone? I could totally see him doing like select all that apply type of thing with this exact concept. So make sure you understand what entropy is and at least know the word microstate because he might throw that in there into a problem. All right, next one. This is getting into spontaneity. And so when we're talking about something being spontaneous or not, what is the term or the like thing that we're trying to solve for? I don't know if I asked that in a good way. Not entropy or enthalpy, but there's a new thing that we added, delta G. Yeah, Gibbs. Gibbs is what is the like end all be all. Will this thing be spontaneous or not? And as a review, spontaneity doesn't have to do anything with the speed of the reaction. I could also see him throwing that in there as a true or false. And as an example that like, for some reason, I remember that off the top of my head, if you think about a diamond turning into graphite, that takes like millions of years, but it's technically a spontaneous reaction. So that's an example of something that is spontaneously happening. Like if we leave it here for a million years, it will happen by itself, but it's obviously not fast. So that kind of helps me understand that. Yeah. Nothing to do with the speed. Yep. Only with, do we need to basically input energy or do something to make this happen? Or will it happen on its own? And so we found out that we have this equation here. which is a really big thing in like biochemistry and even like organic chemistry. So this comes back up, and even sometimes in like bio classes, you maybe have seen it. So this guy can get you pretty far with understanding like will something happen on its own. And when we have this, we say that if delta G is negative, then is that can be spontaneous or non-spontaneous? If it's negative, it's spontaneous. Yep. Then if it's positive, it's non-spontaneous. So here's an example. If we said that delta H, the enthalpy, was positive and delta S was also positive, what would lead to spontaneity? Is it big S? So instead of talking about what you're right, but normally this will be hinting at um, what do we have to do to the temperature? Yeah, a high temp, exactly. So with these problems, there's a whole like table that you can memorize of if this and this, then this, if this. I don't think you need to do that. I think it's easiest if you understand how this equation works and we can plug in fake values pretty much to determine will this be positive or negative. So if we said that this is positive, the delta H, that means it's endothermic, right? Which is not good for spontaneity. For spontaneity, we want things to be exothermic, but it's positive delta S. So that means it's getting more entropic. That is good for spontaneity. And if we want this to be negative overall, we would have to be subtracting a really big number here to bring it back down into negative territory. So that means that we would need T to be really big so that the overall thing we're subtracting lets the Gibbs be negative. That makes sense? Cool. So there's a couple conditions, one that will always be spontaneous and one that will always be non-spontaneous. If you ever have a negative delta H and a positive delta S, so exothermic and getting more entropic, no matter what you do to T, that's always going to be spontaneous. And then the inverse, if we had this being positive and delta S being negative, no matter what you do to T, it's always going to be non-spontaneous. We feel good about that? Cool. All right, next one. This is using some like real formulas that we need to plug into. So if you guys know the formula off the top of your head, use it. I'll pull it up real quick. But we have a reaction that is written as that, and we're assuming it's in standard condition temperature. Does anyone know what that is? Yeah, 25 degrees Celsius or 298 Kelvin. And we're given exact amounts of the atmospheres for these gas reactants and products. And so what we can do here is we can find Q, because we don't know if we're at equilibrium, right? So we're going to go and find Q. And then once we have Q and we have the standard delta G, we can find the non-standard. And so that's what this is asking for, the non-standard Gibbs free energy. So spend a few minutes working on this one. I think the formula we have to be using is this one. Um, minus RT ln Q, but let me make sure real quick. Does that look right to you guys? Yes. All right, so spend a few minutes working on this one. Again, a lot of this exam will be formulas that you're given on the formula sheet, and all you got to do is plug in numbers. But the big thing is to make sure you're canceling out units, because that's an area you can make pretty easy mistakes. Okay, I messed one thing up. It's a plus, not a minus here. Sorry about that. So from there, I'll start working on it up here. Really not a whole lot that's tricky about these ones because all we're doing is plugging in numbers. So we know that the standard delta G is negative 13.2. We're adding that to R times T times ln of Q. So let's find Q real quick. Q is, again, products over reactants raised to their stoichiometric coefficients. And so we have the methane and oxygen given as 1.82 or as 2.3 atmospheres. So the only product that we have is CO2, and that one doesn't have a stoichiometric coefficient. So it's 1.82 divided by 2.3 for the methane times 2.3 squared for the O2, because again, that has a 2 in front of it. So we can do this real quick. So overall, we could also turn this into 2.3 cubed if you wanted to. This is going to equal 0.150 roughly. And now we get to use R and T. So R is 8.3145, but we're using kilojoules. So we're going to have to turn that into 0.008 point or 813, whatever. So I'm going to write that as 8.3145 times 10 to the negative 3 times T. And again, that's in Kelvin, so 298.15. Yes, this would be, yeah, once we turned it into kilojoules, times ln of 0.15. Yes, exactly. So since liquid water is a product, it's not going into Q.
Would you do LN first?
Yeah, ln of 0.15 first, and then multiply it by those other things. So it's negative 13.2 plus, once I did all this, I got negative 4.70. So overall, our answer is the non-standard delta G is negative 17.9. And the units for that are kilojoules per mole. Do you feel okay about that? Again, I would make sure, look at the formula sheet that he's been giving you all these exams. Make sure you know what is given on the formula sheet and what's not. I think most of the ones like this are provided though. So should be okay there. All right, next one. I don't have too many left, but at constant pressure, determine the delta S of the surroundings when the delta H of the reaction is negative 306.5 kilojoules at 27 degrees Celsius. So this is another formula that this one I'm not as certain if you're given, but the delta S of the surroundings is Q of the surroundings over T. And at constant pressure, Q of the surroundings equals the negative delta H of the system. So in other words, we can say that this formula is negative delta H of the system over T in Kelvin.
Why?
What did I do? Flip what part around?
Which equation?
These are the same. This one is the one that makes the most sense. You don't really need to know all this stuff, I guess. This is kind of the more important one, but it is good to know that at constant pressure, the Q
So Q of surroundings is delta E.
is the negative delta H of the system. So does that make sense? If the system is, positive or negative delta H, the surroundings would be the opposite of that. So we're going to take the inverse of it. So for this one, the answer would be if it's negative 306.5 in the system, we're going to make it positive 306.5 in the numerator over I guess what's 27 plus 273 is 300 Kelvin. So we're going to get an answer of 1.02 kilojoules per Kelvin. And those are the units for delta S. Is that okay for everyone? Yeah. Yeah. So if we're told that the delta H of the reaction was negative 306.5, that means that the reaction itself is releasing that amount of energy. So the surroundings are going to be receiving that, if that makes sense. So if something is releasing energy in the reaction, that means that it's going to be for the surroundings gaining it. So that's why it's positive.
And off the system, you would just do the negative 306 minus the something.
Um, I think I think so. I don't know if it's a different formula, but it's you have the right idea where like the system would be gaining that. So yeah. All right, next one. Uh, maybe this is an example of what you were asking there. When 1.5 moles of water undergo freezing at 0 degrees Celsius, the enthalpy change for the process is negative 6.01 kilojoules per mole. Again, that's releasing heat as we go through it. And I'm asking you to calculate the delta S for the phase change. So I think this is what you're asking, because now we're getting the delta S for that reaction. And this formula is going to be, I think, should be this. But we have to be very careful. When you see a problem like this, we're talking about specifically 1.5 moles of water. So they're asking about the exact amount of delta S for this quantity of water that's freezing. And so what we're going to do is we have to factor that in when we're talking about the delta H. So the delta H, again, has the units of kilojoules per mole. So if we have a mole value, we can multiply by that to cancel out moles. So again, we said it was negative 6.01 kilojoules per mole. So per every 1 mole. And I'm going to multiply it by 1.5 moles. So we can cancel that out. So this is 9.02 kilojoules. That's what's going into the numerator now. Over the T in Kelvin. So at 0 degrees in Kelvin, that's 273.15. So that looks good. And I forgot about the minus sign here, sorry. There's a minus. And so the answer to this one is negative 330.2 kilojoules per. Oh, sorry, I put it the wrong way. My bad. It's negative 0.0330. So what I'm going to do in a second, because this looks like a weird answer, is I'm going to turn it into joules. A lot of times this is how the answer will look. So it makes more sense if we multiply this by 1,000 and write it as negative 33.0 joules per Kelvin. Does that make sense to everyone? Cool. Yeah, I find this stuff to be pretty boring as well. So it's kind of like you got to use these formulas, plug it in right, and hopefully it should be some not too hard problems. And then this last one, we can go through this one pretty quick because this is very standard stuff. It's like the Hess's law stuff from Chem 131. So we're told that when we have a reaction, we can calculate the delta S standard for the reaction by using these tables of values for the reactants and products. And again, the way we do that is we multiply the products by their stoichiometric coefficients and its products minus reactants. And so I have a table up here, and I wanted to be tricky, so I didn't give you the exact chemical reaction. So we have to kind of figure that out ourselves. So I'm saying between hydrogen and oxygen in their elemental states forming water. So see, maybe spend a minute on this, see if you can figure out what that reaction would look like with their coefficients, and then I'll show it to you up here. Do you guys remember the diatomic elements from 131? Dr. Brinkelhoff, mnemonic.
That is my.
So
And this is
The-
the products.
yeah, so H and O, both in their elemental states, are diatomic. So it's H2 plus O2 going to form water. And so we have to balance this by adding a 2 from the water and then a 2 from the H2. So he might be annoying like this and do something like this on the test. He's more likely to give you the reaction already formed. But this is important because we need to have the stoichiometric coefficients to do this. So I'll go through this real quick. Again, it's products minus reactants. So we have 2 times the H2, and that's given as, we're going to be using this table on the right. I don't know what the one on the left is. So use these values. So it's going to be 2 times 130.6 plus, or sorry, I'm sorry about that. Should be, we're doing H2O first. So it's going to be 2 times all of that H2O. So 2 times 188.84 minus the sum of these ones. So this is going to be 2 times the H2. So 2 times the 130.6 plus O2 by itself. So 205.07. Is that okay for everyone? Products minus reactants, always multiplying the thing by its coefficient. And so this answer comes out to be, what do I put it in here? 377.68 minus 466.27. So overall, negative 88.59 kilojoules per mole. Is that good for everyone? Sweet. All right, yeah, I know this stuff is not the most exciting, but good to know how to do it. Does anyone have any questions about this or the other ones?